Imagine you're a linguist traveling to an isolated land with inhabitants who speak a totally unknown language. Quine called it Arunta. Picture walking on a path with one of the inhabitants, and a rabbit suddenly pops out from the vegetation. As it rushes by, your Arunta companion exclaims, "Gavagai." Quine's deceptively simple question asks, what do you think Gavagai means? First, the obvious answer, the rabbit, of course, but not so fast. Does it more generally mean a rabbit, or more specifically, this particular rabbit? Or maybe it's referring to some aspect of the rabbit, like its shape, texture, or color. Or one of its parts, like the tail or the ears. Then again, maybe it's about what the rabbit is doing. If so, does it mean hopping, moving, or fast? And how about this? What makes you so sure it's even about the rabbit at all? I think you get the picture. Quine's name for this problem is an indeterminacy of reference, which is just a fancy way of saying it's not clear what words refer to. The interesting thing about this thought experiment is that we've all actually performed it in one form or another countless times over the course of our lives. And by far, the time we did it the most was as a child learning our native language. Being born into this world as a human is like being a linguist dropped into the land of Arunta. But unlike the conundrum presented by Quine, it turns out that babies, and adults for that matter, have many tricks up their sleeves to crack the reference code. To set this up, let me share a nice little parable. It's sometimes attributed to Francis Bacon, but actually the source is unknown. It's about a group of village elders vigorously debating how many teeth a horse has. The elders draw on ancient texts and put forth elaborate theological arguments, but after 13 days, there's absolutely no agreement. Then, on the 14th day, a young friar comes along and boldly suggests a solution. The elders could just head to the barn and actually look in a horse's mouth. As the parable goes, the friar was scorned for making such an audacious suggestion and challenging the elders' authority. On the next day, the question was declared to be an unsolvable mystery. One of the morals of this story is that many puzzles are cleared up just by going out into the world and observing how things actually are. In today's lecture, we'll do just that. In the years since Quine, there's been an explosion of research empirically investigating how young children actually map meaning to words in real-life language development. As with other things we've discussed, you'll see that human babies possess some innate and learned heuristics that give them a head start in solving Quine's conundrum. To solve Quine's problem, a baby must be able to actually hear the different speech sounds that compose words. Now, you already know that newborns are innately capable of doing this, so that gets them off to a good start. Janet Werker has argued that these early phonological skills serve as a sort of bootstrapping mechanism for babies to be able to attach meaning to new word forms. This makes a lot of sense if you consider that from ages 6 to 12 months, not only do babies start to narrow their perceptual focus only on native language phonemes, that's also when they begin to understand words in their native language. Comprehending standalone words like mommy or bottle, that's one thing, but parsing words in a sentence is another. One of the major challenges faced by babies in their first year is to identify where one word ends and another begins. Have you ever watched a film in a totally foreign language without subtitles? That's what it's like to be an infant learning language. The good news is that babies have some powerful learning tools that help them crack the code. In 1996, Jenny Safran, then a graduate student at the University of Rochester, published a paper that changed the way we think about how infants learn language. I'll give away the take-home message up front. She found that 8-month-old babies are able to extract statistical regularities in continuous speech to identify words and word boundaries. For adults, identifying word boundaries in our native language seems trivial. But try to see things like an infant. Consider the example that Safran used to set up the problem. Imagine saying pretty baby to an 8-month-old. I'll say it again, and notice that the two words run together, pretty baby. how are infants supposed to know that they are hearing two words, pretty and baby, and not one word, pretty baby, or even three words, pre, tibe, and bi? Safran's hypothesis was that babies solve this problem by paying close attention to what syllables co-occur in their native language. To test this, Safran presented 8-month-olds with a 2-minute string of English syllables spoken in unbroken succession, sounding like this: Ti-ba, ku-ba, ta-di-ba, gi-ba, du-ba, ki-ba, da. It went on like that for 2 minutes. The key manipulation was to vary the probability of certain syllables co-occurring with one another. For example, over the 2 minutes, whenever there was a B sound, it was followed by a da sound 100% of the time. But whenever there was a ku sound, it was followed by a pa sound only 33% of the time. If babies use these transitional probabilities as cues to word boundaries, they should be more likely to learn that bida is a word than kupa. After all, bida always goes together, but kupa does not. That's great, but how do you measure this? Safran had a creative solution. She borrowed a procedure from her advisors that involved coupling words with a blinking light. Previous research had shown that babies are naturally drawn to blinking lights and will look longer at them if the light is accompanied by some interesting auditory information. The idea is this: if words are inherently interesting to babies, they should look longer when they hear things that were words, like bida, than non-words, like kupa. Make sense? Well, that's exactly what Safran found. After just 2 minutes of exposure, the 8-month-olds looked longer at the blinking light when accompanied by sound combinations containing bida than kupa. This suggests that babies actually learn something about the words and word boundaries. Let that sink in. What this means is that young babies are such good pattern recognizers that they can learn what is a word and what's not a word from extremely limited auditory input. This is a very robust finding and has been replicated many times. And it's also been extended in interesting ways. Here are 3. 1, the ability appears to be innate. A Finnish team of researchers has measured electrical activity of newborn brains and found that they also use statistical regularities of syllable combinations to identify words and word boundaries. 2, research by Safran's advisors, Richard Aslin and Alyssa Newport, has shown that the ability to detect patterns in speech probabilities is not unique to humans. Monkeys can do it too. This suggests that the skill is built on mechanisms shared across species. And 3, this pattern recognition ability shows up in other modalities, such as vision, suggesting that it's a domain general skill and not one specifically designed for language. Altogether, the story should be familiar by now. Humans are born with some innate domain general knowledge and powerful learning tools that allow them to get an early jump on learning language. But let's not forget Gopnik, Meltzoff, and Kuhl's third mechanism. The burden of learning word boundaries does not fall on infants alone. They get plenty of help in the form of unconscious tuition from adults. If you've ever talked to a baby, you've probably noticed that your speech does a funny thing. For most people, it becomes very sing-songy and it greatly exaggerates certain sounds. This distinct speech pattern was called motherese in the 1970s, but it's probably better known by a term that's been around for over a century: baby talk. By exaggerating phonemes and accentuating certain words in a sentence, adults are unwittingly giving babies cues about the structure and rhythm of their native language. This information helps babies identify words and pick them out in the flow of syllables. If you combine that with babies' excellent pattern recognition skills, the problem of identifying words and sentences becomes so much simpler. So now we've worked our way up to Quine's conundrum. Once a baby has identified a word, how does it know what it means? It turns out that they get a lot of help from 2 places. Not only do adults provide useful hints to clear up ambiguities, but babies themselves have some powerful biases and heuristics that help constrain potential meanings. We'll talk about these biases and heuristics in this lecture, and we'll cover the social hints later. Ellen Markman of Stanford University was one of the first developmental psychologists to systematically study the cognitive constraints on children's early word learning. She identified 3 in particular that greatly helped children solve Quine's problem: the whole object assumption, the mutual exclusivity bias, and the taxonomic assumption. Let's take them up in order. The whole object assumption refers to the tendency of a language learner to think that a word refers to a whole object and not its parts. So when babies hear the word bottle, they will assume that it refers to the whole thing, not just part of it, like the plastic base or the nipple on top. This bias is built on another, more basic bias for how babies perceive objects independently of language. Elizabeth Spelke and Philip Kelman argue that babies have an innate tendency to perceive objects as connected wholes and not as combinations of individual pieces. Back to the baby bottle example. They visually experience it as one thing and not as something with 2 separate parts. To prove that babies perceive objects this way, Kelman and Spelke did a study that presented 3-month-olds with a rod that moved back and forth but had the center part of the object occluded. They used a procedure called a habituation paradigm that's similar to what we've discussed with infant phoneme perception. Remember, the idea is that babies get bored with a thing and they look away, but then if you change something up, the babies notice it, they get interested and look again. It's the same idea with this study. During the preliminary habituation stage, the experimenters showed the infants the stimulus